Okay, guys, you're going to pay attention or what? Right, so actually, it's the last talk, my final talk, and also the hard work has been done a little bit. So today, it's going to be a little bit easier, I think, and I want to show you some very nice results about the fluctuation of the Boltzmann function in the Hammersley process. But first, we're finally ready to actually introduce the Boltzmann function and show some properties, since we have these semi-infinite geodesics. So, what do we do? What do we know from last time? If we have some direction, let's say alpha, then at each point there exists, at least at each Poisson point, there exists a unique minimizer, semi-infinite minimizer in the direction of alpha, a geodesic. And also these geodesic, they will coalesce with probability 1. So here's this minimizer, here's the other one, they will come together, and I can take some point, or maybe some other point, doesn't matter, along this line, and then define the Boltzmann function from x to y. So it's a function on R2 times R2, and I define it as a difference between L from C to Y minus L from C to X. And C being this point of coalescence, so it's also a function of X and I. And of course the point is that it doesn't matter which point you take after the coalescent point, because both pieces will just increase or decrease with this part, and so it cancels. So now this function is well defined for all x and y in R2. And it has some nice properties. So for example, if x is smaller than or equal to y, so coordinate wise, and this alpha is going down like this, then we have that the Boltzmann function is positive. And the reason being that if y is here, then LC of y is bigger than LC of x plus Lx of y. X of y, Lx of y is now defined because x is smaller than y, and this is a positive number, and that's it. So that's nice. It's increasing in this direction. So another important thing that Leandro already said is that it's additive, the Boltzmann function, and not super additive or sub-additive. And that's maybe a little bit surprising, but if you see the picture, you will realize that it's actually a triviality. So let's have another point z here, and of course it will also coalesce somewhere, like this. So now I can write the Boltzmann function from x to z plus the Boltzmann function from z to y. Well, I have this joint coalescence point for all three of them. So this will just be the L from C to Z minus the L from C to X, and then plus the L from C to Y minus the L from C to Z. And you see it immediately that these cancel. The Z drops out, and what you end up with is the Boltzmann function from x to y. So it really is a triviality. Okay, that's the additive part. Then there are some distributional aspects of the Boltzmann function, which are also not that hard. So one thing is that you can look at the Boltzmann function and add some vector z. So this is a function of x and y, and as a function, or as a process, this of course has the same distribution as the original one. Right? Because all you do is translate the Poisson process, and that doesn't matter at all. And the same thing holds for this transformation that we had. We know we can do that, and that should have some consequence for the Boltzmann function. So the easiest way to write that down is to look at, at this process. We fix the origin. So now it's only a function of one vector in R2, and this function has the same distribution as if you would go from the origin to r times x and t over r for any r bigger than 0. And again, the reason is obvious. This map, it maps the Poisson process into a same Poisson process with the same intensity. And also every upright path is transformed into an upright path. So the whole thing, if you couple them like that, they're exactly equal, these things. So they have the same distribution.
Does that depend on the linear character of the transformation? I mean, you can have any non-linear transformation.
Well, it's not so easy to have a non-linear transformation that preserves all the upright paths. It has to be volume preserving, and it has to preserve the upright paths. So I'm not quite sure that it uniquely defines this, but it's not so obvious what you should choose. In principle, it doesn't depend on linearity of the function. Okay. There's a technical condition. That's the hardest one, and that's why I won't prove it. So the hardest condition is actually that if you look at the expectation of the Boltzmann function, and then let's say from 0 to 0, 1, no, to 1, 0, that's better. It doesn't really matter. So this expectation is positive, and this is not so hard. And it's small in infinity, and that's a little bit of work. So you actually need to use these exponential bounds we had following from the delta straightness. So the delta straightness is important to prove this result. And we had these exponential bounds, and then you could then you can make sure that you have a finite expectation. In fact, I won't do that today. You can show that as a function of this parameter, so let's say you go from 0 to xt, and you look at this as a function of x for fixed t, then you have an ergodic process. And that also requires some work, but I won't do that today. Okay? So one more little bit obvious fact.
You mean a sum of ergodic difference? So the increments are stationary.
Right.
So the
And
would be the sum of the increments.
it's true. So it's like the increment of a like the integrated ergodic process. There's some type of weak mixing between the increments if they're far away. Okay? And now, so that's what Leandro did also, that you can go in the direction alpha, but you can also go the other way and define the Boltzmann function like that. And by symmetry, that shouldn't make a lot of difference. So what you get is that you do b of minus alpha xi, xy, then this has the same distribution as b of alpha y of x, y to x. So it's switched around. And this is exactly equal to minus from x to y. And this is not just a distribution, this is just true, and that's also trivial because, well, you just switch these two things. So that's clear. Okay. So these, most of them are relatively straightforward. Actually, apart from this one. And then there's one other property, and this property had to do with this kind of fluid system that Leandro was talking about. So it has a certain Markovian structure, this Boltzmann function, and that's what I want to show you. Okay. So let's make a picture. So we have time s here and time t, and then here we have let's say the point 0s. And here you have the point xt, like this. And for our picture, it will be important to have, well, let's draw it here. So what I'm going to do is I'm going to relate the Boltzmann function at xt to the Boltzmann function at time s in some way. And for that, you can imagine that in the picture. So let's write the result and then extend the picture. So the result is the following. If you take the Boltzmann function from 0s to xt, then this is the same as the supremum over z smaller than x of the Boltzmann function from 0s all the way up to zs, and then plus the L from zs to xt, like this. So what happens is that you take the supremum over all points to the left of x here, and then you end up, let's say, at some z, and then you add the L from z to xt. So this is interesting because this part of the Boltzmann function, it lives at time s, and therefore it only depends on the Poisson process below time s, right? Because alpha is going down. So it only depends on this past. But this process, this is between s and t, so that only depends on the Poisson process here. So these two things are independent. So you have two independent processes, and then you maximize some parameter, and then you end up with the Boltzmann function at time t. So that's like a Markov step. You kind of you have the Boltzmann function here, then you update it with an independent thing, and then you get the new Boltzmann function. And because of translation invariance, we know that the distribution of the Boltzmann function here is the same as the Boltzmann function there, and therefore this Boltzmann function has to be like a stationary process corresponding to this Markov process. That's exactly what Leandro was saying. And in fact, that's how he kind of proved that the Boltzmann function should be equal to the stationary measure that we know. So the stationary measure, we kind of just, by a miracle, we take a good guess and we check that it's a stationary measure. And then this thing, well, you need some more work, but this is basically the idea. This thing shows that this Boltzmann function should correspond to that stationary measure. And the same will be true in this Hamilton process. So this is important property. Now, since we're working with Boltzmann functions, I'm sure that we need these semi-infinite geodesics somehow, and here as well, like this, and maybe even from Z, like this. So there's a point here that this semi-infinite geodesic hits the time S, let's call it Z star, like this. And now we have, the picture is good enough now to prove this statement, what we have. Okay. So the first thing we notice is that the Boltzmann function from 0s to xt, it's actually the same as the L from, let's call this coalescing point C, to be original, So the L from C to xt minus the L from C to 0s, like this. And then since this is a geodesic coming from xt, the length from L from C to xt is the same as from C to Z star, and then from Z star to xt. So this is L from C to Z star plus L from Z star to xt minus L from C to 0s. But then this difference between these two is exactly the Boltzmann function from Z. No? It's slightly disturbing. No, it's correct. That's good. Yeah, from 0s all the way up to Z star. And then plus L from Z star to xt. So this means that the Boltzmann function is certainly smaller than this supremum. Yeah, because we have an actual Z for which it's equal. And this is the supremum of all Z. So we've proved that this is smaller than this supremum. And now what I'm going to do for every other Z, I'm going to show that, in fact, this is smaller for the Z. So that's the second step. So what I'm going to do, so again I'm going to write down the Boltzmann function from 0s to xt. Well, so I could have copied it, I guess. C to xt minus C to 0s. And then, so we're interested in the L from C to xt, and of course that's bigger than going from C to Z and then from Z to xt. So this is bigger than L from C to Z plus L from Z to xt minus L from C to 0s. Then I'm not done, I think, because this difference is just the Boltzmann function from 0s to Z, and then plus the L from Z to xt. So here it says that indeed the Boltzmann function is bigger than this value for every Z, and therefore it's also bigger than the supremum. So in fact the proof shows two things. This is equal, and also the maximum is exactly where the infinite geodesic crosses the line. Okay. And like I explained, this is a Markov property of the Boltzmann function, and it allows us in certain special solvable cases to actually know what the distribution is of the Boltzmann function. And that's the most important contribution of this formula, of this whole idea with the interacting fluid system. Okay. So what I would like to do now is step away from the general case and go to the special case where all the weights I have weight 1, which is called the classical Hammersley process. And I want to show that there are kind of, well, what we call hydrodynamic methods to prove that the fluctuation in that case is of the order, well, 2/3 or 1/3, depending on what you're looking at. So I'm taking the special case where, well, I think I wrote it like this. So F is just all the weights are just identically equal to 1. So these paths, they pick up just number of Poisson points. You know, that's all that matters. And what we're going to do is we're going to introduce this fluid system that Leander was talking about, but now in this simpler case it will be a particle system. And the particle system is linked to this function L, and therefore also linked to the Boltzmann function. Okay, so what am I going to do? I'm going to look at a finite box, xt, and then there are some Poisson points, like this. And then what you could imagine is that you start with an empty set of no particles, and then we move up in time, and then you encounter one of these Poisson points. And if you encounter a Poisson point, the particle to the right of this point gets drawn to this value. And if there's no particle, one is just drawn from some reservoir at infinity, or at least outside this box. So it means that here nothing happens, and then all of a sudden a particle is drawn to this point, and then from that time on there will be a particle here, at this place. So we continue, and then we encounter this Poisson point. So we go up like that. Yeah, one is drawn again from the outside. We continue. Then we encounter this one, so the one to the right is drawn to that point, like this. We go up, this one is drawn here, and this one stays like this. So at time t there will be two particles in 0x. We started with 0 and now there's 2. So this is a particle system and it will evolve in time. And the link with what we did before is that the L from 0 to xt is exactly equal to, well, let's call it the flux. Flux being the number of particles we see in the end. Now, why is that so? Well, each particle corresponds to a trajectory, a particle trajectory, and it's clear that you can only pick up one Poisson point in the trajectory because the Poisson points are not ordered in this trajectory. So in the longest path, you can never have two Poisson points from one trajectory. So that means that the number of trajectories is bigger than the number of Poisson points that you can pick up with a northeast path. Right? On the other hand, there's a simple construction that shows that you can pick up a Poisson point from each trajectory. Now, how would you do that? Well, you start here, then you go down until you hit the first path, and then to the left you will catch a Poisson point. You go down again, maybe I should take a different color. So you go down until you hit the first thing, then there's a Poisson point, then you go down to the next path, and then you pick up a Poisson point here, and then you end up at 0. And in this way, each path that's inside the square, you will pick up exactly one Poisson point, and therefore that will be your longest path. So this L is related to the flux of these particles. Okay, now it's clear that if you go on in time, there will be more and more particles coming in, and they will start to accumulate to the left, and so that it won't stabilize somehow. So that's a pity. We don't want that. So what I'm going to do, we're going to adapt this picture a little bit in order to get a stable picture. So we're going to allow to start with a certain number of Poisson points, or of particles. You want the same picture? Why not? So these particles, they are drawn from a Poisson process with intensity lambda. So now we have even more particles, so there has to be some mechanism to allow particles to leave. Right? So these are, well, we call them sinks, sources, and sinks, doesn't really matter. So these are kind of exit points for the particles, and we choose them to be a Poisson process with intensity 1 over lambda. So it's specific choice. They have to be balanced in some proper way. And then I have my Poisson points, like this. And now I'm going to run my particle system. So I already started with 3 particles. Okay, that's nice. Then I go on until I find the first Poisson point. This one is drawn to the left, and continue. And now I encounter this exit point, this sink. So what it means is that the point to the right, it will just disappear. So this particle, it escapes through the left. Okay, so now we have 2 particles left. So this one goes like this. Here a new particle comes in, like this. And then this one escapes again. And this one goes like that, and this one like that. And in the end we will have 2 particles. Is it clear how this particle system works? And you can see now that there is a mechanism that particles come in from the right, but they also leave from the left. So maybe there's some stationarity here. And of course, in fact, there will be.
Why the second particle couldn't go above?
This one?
Why it has more, it's going to the...
There was a sink here.
Okay, so there is like a...
There was a, well, maybe I should have a different color again. But so here there's this Poisson process of sinks, and a sink always pulls out. In fact, if there's no particles and there's a sink, then one is drawn like this. So it comes from outside and goes there. That's also possible. Okay, so this is a new process, and now we can define a new L lambda of the point xt. So this will always be defined from 0, let's say. You start in 0 and then you go to some point xt. And this L is also the flux of this new system. Flux being just the number of particles that flow through this square. So in this case it's 4, I think. Huh? Okay. And so it's somehow similar to this picture, and the flux was related to our original L, and now we have a new one, L lambda. It's also the flux of the particles, but this can also be written in a kind of longest path way. In the following way, you just what you do is you want to take a longest path, but you're allowed to either pick up these sources or pick up these sinks. And you're allowed to do that. So for example, I can have a longest path that goes like this. It picks up 2 sinks, and then it picks up this point, and then it goes to xt. So it's a bit similar to what we've seen before, but you just have more options. You can also pick one of these things. Well, it's a new function. It's a different one. And what I'm trying to convince you of is that, looking at the flux of the particles is in fact the same as defining this longest path, where you're also allowed to pick up weight along these 2 axes. So that's what I'm trying to convince you of. And so why is this true? Well, it's the same argument as before, because clearly you can only pick up from each of these paths, you can only pick up one source, either on this axis or on this axis or this one, but you cannot pick 2 of these because they're not in the right order. So again, the longest path will be smaller than the number of paths that's here, the number of particles, and it will be equal, well, simply because you have a similar construction. You can go like this, go down to the Poisson point, like this, go down to the Poisson point, and then like this and pick up all the sinks. And this way you will cross all the paths and pick up one thing from each path. And you can do the other way as well. Go like this, pick up this Poisson point, go like this, and then pick up these three sources. That's also possible. So here, it's kind of relevant that there is this interpretation of a particle flux, but also of a longest path. So what's immediate, it's also important, is that this is bigger than the original one. Yeah, because, well, you can pick up more weights. You're not only allowed to pick up Poisson points, you can also pick up these sources of things. So we have increased. Okay. And now there's a miracle. Right, so I have this very specific construction, Poisson lambda, Poisson 1 over lambda. Of course, I take them independent. And I take them independent of the Poisson process of points with intensity 1. That's in the plane. And then we have a Burke-like theorem that says that, well, it has a couple of statements actually. So if I look at the number of particles here at the top, so I could write it as L lambda xt minus L lambda 0t, like this. That's just the difference between this and this. Then this is again Poisson distributed with intensity lambda. So on top we still have Poisson. And then there's another one that's here on the right. We can look at that process. So that's L lambda. Yeah, so this should actually be seen as a function of x. So maybe it's better to write y and write it as a function of y. And then this increasing function behaves like a Poisson process with intensity lambda. Huh? So if you go like this, you pick up more and more particles, it's a Poisson process. And here we would have something similar. Now there's a time s, and we go from, and we look at the difference between xs minus x0. So this is this side here, when I go up like this, and then this is also a Poisson process with parameter 1 over lambda. And then there's a third process, which is the process of these corners here. That's it, I think. So these are, each path has two types of corners. One is the original Poisson point, and then one is this other blue point, right? And these blue points, they are Poisson 1. And all three of them are independent. All three of these things. So that's a slight miracle. It's like the reversibility of the entire picture. Right? You could make the same process using the exit particles here, the entrance particles here, and then these blue dots as new Poisson points, and then you could write down the whole process like this, and you would end up with the same thing. So it's like a reversibility. And you can prove this simply by doing a generator calculation. It's a little bit complicated, you have to keep track of these three things at the same time, but you can do that, and it's basically an analytic calculation. That's the big advantage, of course. If you have an option for a stationary measure, then you can check it relatively easily. It's just a matter of calculating. So that's here as well, and I won't do the calculation. So we have, well, stationarity when you start with Poisson, but we have even a little bit more in the sense that here again it's Poisson 1 over lambda. In fact, this reminds me of the little trick that Leandro did, where you had this downright path, and then you make a switch like this, and you prove that this thing and this thing are still independent, and here there's also some nice x, some third variable. That's completely similar to what happens here. Yeah, because you start with independent, independent, and you end up with independent, independent. So for example, if you now move on to the right, if you look at this piece of the process, then whatever happens here is somehow encoded in these, in this line. And we know that it's independent of that part. So you kind of maintain the independent structure that you want. The only thing is that this really was just one step, one flip, and you can do an easy calculation. That's not so easy here because it's continuous, so there's some more work. Okay. So this is really nice, and of course this, again, determines the Boltzmann function. Right? The Boltzmann function between this point and that point must be, because, well, I haven't shown that yet, I guess. Maybe I won't. And so, yeah, maybe I should. This. What I'm trying to say is that this L lambda satisfies the same updating rule as the Boltzmann function. And that's why they coincide. So, yeah, a little bit subtle. Well, let's write it down anyway. So L lambda, let's say from 0 to xt, is the same as the supremum over z smaller than x of, let's call it nu lambda of z plus L from z0 xt, and this thing here is Poisson lambda. So what did I do? I'm cheating a little bit here. I'm skipping a few steps. So the first thing I did is to kind of extend this left-hand side all the way to minus infinity. And that's allowed because you keep having independence in the same Poisson structure here. So you go down like this. And then what I notice is that if you want to have the longest path, so this blue path, then you first pick up some points here, and after that you go into the bulk, let's say. Yeah?
So this Poissonian distribution must be dependent on y, right? No, the first one. No. I'm still on the.
Oh, this one?
This L lambda y0, and then you go to the last the L lambda from 0 to t.
Yeah.
So this is a Poisson distribution.
Well, it's a Poisson process. That's what I meant to say here.
Okay.
It's a Poisson process with intensity lambda.
Yeah.
So it increases with y, of course. So the expected value is y times lambda, for example. And the point is that if I move this to the left, then you keep a Poisson process here. In a way, it doesn't matter. Yeah?
Okay.
In the supremum, the z goes all the way back to minus infinity?
That's right. You can do that.
But then the nu has to count negatively on
Yeah.
that? Okay.
That's right. It will count negatively like in Leandro's case. In fact, you can write this as L lambda from 0 to z, I guess. Yeah. Where, since you go left, this will be negative in a way. But I don't want to go into, it's not so important for what I'm going to say afterwards, but I just want to give you a feeling that there is this type of supremum going on here. You first pick up something from the bottom, and then you go through the Poisson field. So that's exactly what it says here. And you first pick something up, and then you go through the bulk, and it's the same formula as for the Boltzmann function. So in fact, this process that we have defined here, it satisfies the same Markov rule as the Boltzmann function. That's very relevant because in that way you can prove that the stationary distribution that we have calculated here must be the same as the distribution of the Boltzmann function. Because there can be only one stationary distribution with a certain intensity. But so I won't use this formula a lot, or not at all even. Okay. So now we can do some calculations. So there's a theorem. Maybe I should write it well. There's a theorem that says the following. So it's like part one of a variance formula, or exit point formula. What does it say? It says that we can say something about the variance of this L lambda x and t. The variance is the number of points. And we can do it in the following way. This is equal to t over lambda minus lambda times x, and then plus 2 times the covariance. Now I'm going to introduce for myself, a little bit easier notation. So I will call this bottom part, I will call it the south, and the top part the north, like this. And then I guess there's also the west and the east. So these are the sides of the square. And then what you get here is the covariance between the south and the north. So you can imagine that they are dependent, right? If you got a lot of points here, you will still have a lot of points there. So there's some kind of covariance structure, and that's related exactly to the total variance of this thing. Okay. So how do you prove a thing like this? Well, note that the L lambda of xt is just the number of particles in the square. That's the same as whatever's on the west side plus whatever's on the north side. And 1, 2, 3, 4 you get here. So it's the variance of the west and the north. So that's the variance of the west plus the variance of the north plus 2 times the covariance, like this. Okay, that's nice. Not very useful, it seems. Now we make a next step. We're going to say, well, the west is actually, since the west plus the north is equal to the south plus the east, it's just another way of calculating the same flux. I can replace variance of the west, variance of the north. I can replace this by the south plus the east minus the north. That's the same. And you might say, okay, what does that help? Well, the east, according to Burke's theorem, the east is independent of the north. There were 2 Poisson processes and they were independent. So that covariance drops out. And then you end up with the variance of the west minus the variance of the north plus 2 times the covariance between the south and the north. And the variance of the west and the variance of the north, we can calculate them explicitly because we know that this is a Poisson process and this is also a Poisson process, so the variance of the total number is just known. This is Poisson process with intensity 1 over lambda times t, so you get the variance t over lambda, and this is total expectation is x times lambda, so you get minus lambda times x. Okay, so that's that's nice. We have this relationship between this variance and this one, and you can also immediately kind of guess from looking at this formula that for a special choice of lambda, something nice might happen, right? So if I choose lambda to be the square root of t over x, then the deterministic part cancels. It's 0. So that might be some kind of special characteristic direction or something.
I don't think you need to use the Burke's theorem to top. You might get variance of L equals to this linear terms plus 2 times covariance of S
with L lambda.
with L.
Let's see.
Advance with L.
So you get that.
Just by manipulating, L as a sum
Of the west and the north?
of the west and the north, and
Yeah.
also as a sum of the sum, in a bit different way. What I want to say is that a similar formula should hold for the general
For the general case.
case.
But then you would have the covariance between the south
And L.
and the total L lambda.
Yeah.
Yeah, I think I've seen that as well. Okay. In itself, this formula, of course, is not that useful. The point is that we have a different formula for this covariance. That's what we're going to see. So there's a different way of calculating this covariance. In fact, there are 2 different ways. Okay. So how am I going to do that? Yeah. So I'm going to define an exit point for my L lambda in the following way. It's not so hard to see that the L of lambda, since you can pick up points from this line or points from that line, and then you go through the bulk, and the maximum of that is L of lambda, it means that L lambda of xt equals the maximum of 2 things. It's the supremum over z between 0 and x of, well, let's say the Poisson process, let's call it the Poisson process, nu lambda z plus L from z0 to xt. Yeah, so what it says here is you pick up some Poisson points here, and then you go up through the bulk, and you can maximize over that point z. But you could also do it the other way, going up, that's also allowed. So you can have a supremum of s between 0 and t, and then there's a different nu, slight abuse of notation, that's called nu of 1 over lambda, that's the Poisson process on the left-hand side, and you can pick up s there, and then you go from 0s to xt. Right, so there are 2 ways you can take 2 supremas, and the maximum one will be the value of L of lambda. And then we define an exit point. Well, you can kind of guess, because it should be the point where you leave the axis, but we're only interested in the bottom part. So what I'm going to define is z lambda plus of xt. What is it? Well, it's 0 if the supremum over the s of this whole thing is strictly bigger than the supremum over the z between the x. Right, so if the maximum is attained here instead of there, then we just say the exit point is 0. And in fact, the exit point will be somewhere here on this line. And otherwise, we define it to be the largest value of z in 0x, such that L lambda xt equals nu lambda of z plus L of z0 xt. So what does this mean? It means that we go as far to the right as possible and then go up to this point and still have the maximum value. So this is called the exit point. And it turns out that there's a connection between the expectation of this exit point and the covariance between the south and the north. Or in fact, between the south and the total length as well. So let's see how that works. Okay. So another theorem, part 2. Of this theory here is that the covariance between the south and the north is equal to lambda times the expectation of this exit point. That looks pretty cool. Let's see why this is true. So what we're going to do is we're going to change the Poisson process in the south. So there we had a Poisson lambda, and then we're going to add, let's say, an independent Poisson epsilon to the south. So we end up with S of epsilon. And so again, there's a slight abuse notation. S of epsilon represents the total number in the south with this new Poisson process, but it also represents, the whole fact that there's this Poisson process on top of the original one.
Independent, I assume.
Independent, yeah, independent of what we had before, of everything. Okay. So now, when you have this new south, there's also a new value, so there's L lambda epsilon, right, that uses this new Poisson process. So there are new distances, and they will be bigger in general because you got more points, right? And also there's a new north, N of epsilon. Okay, so what we're going to do is we're going to look at the expectation of the north, and then we're going to take the derivative with respect to epsilon in epsilon 0. And we're going to calculate this expectation, this derivative in two ways. And in one way we'll get this thing, more or less, and in another way we'll get that one. So, it's a little bit surprising, let's say. Okay, so how do we do this? Well, let's just calculate the expectation first. Simply by conditioning on what happens in the south. So, we condition on the south having n points. So the probability of that is, the south has expectation lambda plus epsilon times x. And then like this, you get e to the minus lambda plus epsilon x, like this. This is the probability of having n Poisson points. And then we need to take the expectation of this n epsilon given that S epsilon equals n. Like this. And now there's a very important realization that you have to make. And that is that this thing here, it does not depend on epsilon. Because if I know that the Poisson process has n points, then they're just uniformly distributed, and I lose all the information about epsilon. So this is exactly the same as if I would just take the original n and s. Is that clear? So by conditioning you lose the dependence on epsilon. And that's very nice because now I can just calculate the derivative. This is just a given function of epsilon. So, calculate the derivative. By the way, we did this for n epsilon, but this holds for any function of the Poisson process, of course. Hey, you could always do a trick like this. So, for example, as Leandro was saying, if I would just put L of lambda here, I would get the same thing. It would also be true. But let's see what happens now. So I have to take the derivative with respect to epsilon. And then fill in epsilon 0. So there are two epsilons here, there's this one and this one. This one gives me an extra n. So it's xn n factorial e to the minus lambda times n times the expectation of n given s equals n, like this. And then there's another one that's this epsilon, so it gives me a minus x this should be lambda x. And then again times the expectation of n given x equals n. And then we sum up. Right? Okay, now look, this n I can put it in here, and then I just get the expectation of s times n. Is that clear? Right, because s equals n, so this is like the expectation of s times n. Okay, that's cool. And then here, well, there's this factor x. Yeah. And I'm missing a lambda somehow. That's right. I'm missing a lambda because I've been careless. If I take the derivative, I get a factor of n, that's this one, but I'm stuck with lambda to the n minus 1, so that's lambda to the power n and then a 1 over lambda. Like this. Yeah, that's slightly better. So I get a 1 over lambda here. Here there's a factor of x, so I get minus x times, and then, well, this is just the probability of s being n. Expectation of n given this fact is just the expectation of n. Like this. And now I notice that the expectation of the south is, well, the south has a Poisson intensity lambda, so it's lambda times x, the expectation. So I get 1 over lambda, and then I would get lambda times x here, which is the expectation of the south. And this is exactly the covariance between the north and the south. Yeah, it's just what happens. Yeah, so this derivative equals this covariance. Okay. So this is clearly, by the way, we use the fact that we have quite good knowledge on the stationary state, right? This explicit calculation, well, it only works because we have this nice Poisson structure. And then it works out. Otherwise, you need to do something else. Okay. Let's take this out. And remember the result. So the derivative is 1 over lambda covariance between the north and the south. And now we take a different approach to this derivative. Different approach is that we will look at the expectation of n epsilon minus n. And note that this is always a positive, because I added this epsilon process of points. So we have more points, so we also have more particles in the end. Okay. And then we're interested in something of order epsilon here. Right? So if we think about this extra Poisson process, well, you can have 0 points extra, and then this is just 0. You can have 1 point extra, and that has order epsilon probability. You can have 2 or more points, but that's already order epsilon squared, to have 2 points in the bottom. So in fact, the only thing that's relevant is if you have 1 extra point. That will give you the order epsilon term. And 1 extra point in the south. Okay, and this extra point, so 1 extra point. Let's say it's at z. In fact, we know the distribution, of course, is just uniform over 0x, this extra point. Right? Okay, now let's see. So here I have a picture. Let's make it there. So here we have xt, and then we know that the total length of the path, it goes all the way up to here, and then it goes up. And this is like the z plus lambda xt. It was the furthest away to the right as I could go. That means if I would go a little bit further, I would go at least one down. Yeah, because I would have gone too far. Is that clear? Okay, so now I get this extra Poisson point. Now suppose it's somewhere here. What would happen to the total length of the path? Well, in order to use this extra point, I would have to continue all the way up to there, but then I know that the original path would be at least one lower. So it wouldn't help me at all to pick up this point. Is this clear? So that means that the total number of particles would stay the same. That means that the north will stay the same as well. The flux stays the same, the west doesn't change, so the north will stay the same if this happens, if z is over here. And that's also true if this point is exactly 0. That means that you cannot go here because you will lose at least one point. So the same reason, then it will just never help you, this one extra point. However, if the extra point is here, well, then it's automatic. You just take the same path and it will be one bigger because you get it for free, this extra point. Is that clear? So in other words, n epsilon minus n is in fact the indicator that z is smaller than the original exit point. This is the case when you have one extra point at z. Then this will happen. Now we agree? So now I'm, I guess, almost done. So what is this expectation? So it's the probability that there's one point, and then you smear it out over 0 to x. So the intensity was lambda. And then you integrate from 0 to x, this little z, the location of z. And then you get this indicator that z is smaller than the z plus. And then you do dz, like this. And now you have to take the expectation. The only random thing is here, right? It's in the big Z. That's where the expectation is. So this expectation becomes a probability that z plus is bigger than small z. You integrate this probability and you end up with the expectation. This is not lambda, I'm sorry, this is epsilon, of course. The extra Poisson had intensity epsilon, the extra point. So you end up with epsilon times the expectation of the z plus. Like this. And therefore the derivative, and then here we have order epsilon squared still. I forgot that. That's the case when there are 2 or more points. Huh? Okay, so that means that this derivative is also equal to the expectation of the exit point. And then we have proved this fact here. Yeah, it's pretty cool. Okay, so this variance formula turns out to be the key to show the cube root fluctuations. So let's write it down again. The variance of L lambda xt is T over lambda, lambda times x, and then plus 2 times lambda times the expectation of the exit point. You could have some intuition. For example, if x is rather small, then, so if you have a thing like this, then the exit point will almost surely be, will often be on this side. So this will be more or less 0, and x will be small, and then you get the variance is T over lambda, which is just the variance of this Poisson process. To see that it makes a little bit of sense, this formula. And you can do a similar thing for big X. You can also think about how that will work. And okay. So for us, what will be important is the direction where this is 0. That will be the key. And that's called the characteristic direction. And in fact, the characteristic direction will kind of correspond to the place where the exit point is very close to 0. So this will be small in that case, and therefore also the variance has to be small. That's kind of what's going on. Okay. So I've got like 20 minutes left. That should be enough to do this. So we need a little lemma. We can control in the characteristic direction. We have control in terms of this exit point, but we need a little bit more than that. So we're going to prove for all lambda bigger than 0 that the variance of L lambda xt is smaller than or equal to t times the absolute value of lambda and minus 1 over lambda plus, and then the variance. So this is not xt, this is tt. I'm going to look in the diagonal direction. So the best value for lambda is 1 in that case. That's the case where this will cancel. So 1 is the important direction, but I need a little bit of control when lambda is not 1 but close to 1. So that's why I need something like this, and here I have the variance of lambda L1 tt, like this. No? And how do you prove this? So there's a nice statement here that L lambda of tt has the same distribution as L1 over lambda of tt. And that's simply by switching in the diagonal. Right? You have lambda here, 1 over lambda there. If you switch them, it will be the other way around, and the whole thing will have the same distribution. On the diagonal, of course. Yeah? Otherwise, you would have to switch these two things as well. That means, and it's somehow important, because this thing is much easier to prove for small lambda and not for big lambda. But for small lambda and big lambda, it's the same thing, because this whole expression here is also symmetric in changing lambda and 1 over lambda, because of the absolute value here, and there's no lambda here at all. Yeah? So it's enough to prove this for lambda smaller than 1, and we will use it for lambda bigger than 1. It's, I don't know. There's something subtle there, but I don't know. Okay. Now, note that if lambda is smaller than 1, then z lambda xt is in fact smaller than z1 xt. So what do I mean by that? Let's couple the two Poisson processes. So I start with Poisson lambda, and then I increase it a little bit to have Poisson 1, and then it's kind of clear that if lambda goes all the way up to here, then if you do Poisson 1, you will go at least up to here, because you have more points, and maybe you want to pick up some here as well. But you will never go back. Yeah, because there's more to gain at the bottom, let's say, because there are more points. Is that believable? So that means that when in the coupled case, we have this inequality, and then the lemma follows relatively easily, because we can simply use our variance formula. So the variance formula tells us that this is actually equal to t over lambda and then minus lambda times t. So this is 1 over lambda minus lambda, the first part, and then we get 2 lambda times the expectation of z plus lambda, like this. Now, this here is equal, of course, to the absolute value, because lambda is smaller than 1. Lambda is smaller than 1, so I just forget about it. And z lambda is smaller than z1, so I will just take the expectation of z1 And then this is equal to the variance of L1, according to the same variance formula. Huh? So this is really nice. Okay. Now I can make the final statement of today. It's obvious I'm not as good as Gregorio in timing my talk. I think I just won't make it, but anyway. So what's the theorem? There exists a constant bigger than 0, such that for all t and for all r greater than 0, we have the following result. The probability that the exit point z1 tt is bigger than, let's say, r times its own expectation. Note that the expectation exists because the exit point is always smaller than t. Right? You cannot go beyond t, so there's no problem there. And this probability is smaller than c1 t squared expectation of z1 plus to the power 3 times 1 over r to the third and 1 over r to the fourth. Not quite sure why I have it like this, but it doesn't matter. Okay, so this is a bit of a strange statement. So the probability that your r times the expectation, bigger than r times the expectation, is smaller than something that's integrable in r, that's good. And also the expectation is here again, to the power 3 and t squared. But maybe at least what you can see is that there's a 2 here and a 3 there, so that kind of suggests already the 2/3 in some sense. And we will see that it, in fact, it does. So how to prove this? Well, we simply start by writing down the probability that the exit point is bigger than u. For any u, let's see what happens. And this is equal to the probability that there exists a z bigger than u, such that you pick up Poisson number of points on the bottom, and then you go from z0 all the way to tt, like this, and then this should be equal to our original L1, t of t. Right? It says here that there exists a z, well, let's say equal to z1 plus, such that this length equals the maximal length, because the maximal is to the right of u. Okay. Now I'm going to use the following fact. I'm a little bit annoyed by this term here, because I don't have any control over L. I have control over L lambda, but not over L, so that annoys me a little bit. So I'm going to use the fact that if I take any lambda and I look at L lambda of tt, well, then this is certainly bigger than if I would pick up, if I would first go to z at the bottom and then go from z to xt. Right? Because it's L lambda is the maximum of those things. In other words, I can upper bound this L. So if this is equal to that, then this probability is certainly smaller than the fact that nu1z plus, then I replace this by something that's bigger, namely L of lambda minus nu lambda of z. So I do minus nu lambda of z, and then I get plus L lambda in the point tt, like this, and this should then be bigger than L1 tt. Is that correct? Yeah, we agree? Now we're in good shape, because I have control over the variance of L lambda and also over L1, and in fact I know the expectation of these things because I know what the stationary distribution is. And here, well, if I just couple nu1 and nu lambda, then I would just have a negative or positive Poisson process. So I've got good control on that as well. Yeah? So I'm going to change the sign and say the probability that there is a z bigger than u, such that nu, and then I take lambda minus 1, so with a new intensity, let's call it nu tilde, right? When I couple them, then and I take lambda bigger than 1, then the difference between these two things is just a Poisson process with a smaller intensity, like this. And so I've switched the sign, so this will be smaller than L of lambda tt minus L of 1 of tt. Right? And then of course, if some z bigger than u is smaller than this, then certainly u itself will also be smaller. Yeah? And then I get smaller than. And it turns out this is strange that this would happen for large u. If we pick lambda in a clever way. So what we're going to do is we're going to say, let's look at the expectation of this minus that. And if that's very big, this expectation, then it's strange that this thing is smaller than that. No? So I'm going to calculate the expectation minus those expectations. And I can do that because this is just a Poisson process, so I get lambda minus 1 times u. And then here, what is the expectation of this? Well, so to get the flux, you just have to add this and that. And these are two Poisson processes. 1 over lambda and lambda. So the expectation I can just calculate. Of course, they're dependent, these Poisson processes, but it doesn't matter. Right, so I get minus, and then you get lambda plus 1 over lambda t, and then plus this one, and that's just 2t. Like this. And we can maximize this over lambda. So maximize, and you end up with lambda u being 1 minus u over t to the power minus 1/2. So that's then we've maximized it, and now we're going to hope that this leads to a small probability here because of the difference in the expectation. And in fact, what you can show, and I won't go through all the details because, well, I won't make it, but what you can show is that this difference in expectation is in fact bigger than 1/4 u squared over t, like this. And this is true for all u smaller than, I think, 3/4 t. U can never be bigger than t. And it doesn't make any sense to take u bigger than t, because then it's 0, this probability. And the rest will follow also. It's not a big problem. But this is just analysis. You can just check it, that this is true. And that means that this probability, well, two things can happen. So there's a difference in expectation that's bigger than 1/4 over u squared over t. And that means that the fluctuation away from the expectation from this one or from that one should be bigger than, let's say, 1/8 over u squared over t. One of the two has to have a big fluctuation, at least. Otherwise it doesn't work. So this is smaller than the probability that minus its expectation. This has to be, I think, smaller than minus 1/8 u squared over t. So either this is true or the other one, and that is that L lambda minus L1 minus the expectation has to be, I guess that has to be bigger than 1 over 8 u squared over t. And one of these two things has to happen, otherwise this cannot be true. And the reason is that we have this bound on the expected value. And now we just do Chebyshev. This is Poisson, so that's very easy to do Chebyshev there. You can do a little bit more even, but it's not necessary. And here we can also do Chebyshev, and that's very useful because we will get the variance of L lambda and the variance of L1, and there will be a dependence, but we will ignore it. We will just sum the variances and multiply by 2, so then we have a bound. And for this variance, we have this result and this result. Yeah? So what will happen when you write down the Chebyshev formula is from the Poisson case, or the probability, from the Poisson case we get some constant times t squared over u to the third, and that has to do with the fact that lambda minus 1 is of order u squared over t, so you can just write it down. And so this is from the Poisson case, and from the other case we get so we get this expectation, we get this term, but that's also of order u squared over t for the lambda that we chose. We had a lambda very close to 1, so this is not so big. This is u squared over t squared, and times t is u squared over t. So that basically boils down to this one, and then you end up with t squared, you get the expectation of z1 plus to the power well, nothing, and then you divide by u to the fourth in that case. That's simply the square of u squared over t. That's t squared over u to the fourth. And this comes from the variance, this expectation. And then we're basically done, because now I just choose u equal to c times this expectation, and you fill it in, and you get t squared expectation to the power 3. You see it here, and you see it here as well, because here's to the power 4, but there's an extra one here, so you also get expectation to the power 3. And this is enough to prove the fluctuations, because what do? You now integrate from 0 to infinity the probability that z1 is bigger than r times the expectation, integrated over r, and then you realize that if you divide this by the expectation and you integrate this, you get the expectation of whatever is here, but that's 1, because it's z divided by its own expectation. So in other words, this integral equals 1, but then you use the bound that we have, and you get, what do you get? Now you get something that this is in fact smaller than, let's say, 1/2 plus some constant times t squared, and then the expectation to the power 3. In other words, this sum, or this fraction, is bigger than 1/2, and that means that the expectation of z1 plus is smaller than some other constant times t to the 2/3. So all of a sudden we have an upper bound on this expectation, and with it we have an upper bound on the variance of the same order, also t to the 2/3. So this method has been extended to other models, for example the one that Leander was talking about, but also, especially Timo has done a lot of work in that field to take this method and extend it to other methods. So there I think there's still an example, not 100% sure, I think there's still an example of a function where they cannot do it with analytical methods, but they can do it with this method, you can get the t to the 2/3. That's not true here. In fact, it was already known that the variance of order t to the 2/3 using dive bike range results and all this heavy analytic stuff. Of course, they didn't have the link with the exit point, but that's, well, you can, I think you can also get it. I think the nice part is that you can do it using these methods, you can get this upper bound. Now, I don't have any time anymore. You can use this to bound also the variance of L itself without the lambda, but that's still some technical work. It will be in the notes that I haven't sent yet, but I have to send to you. So I think I should stop here. Thanks.
Any questions or comments?
I have one.
Yeah?
So, I think you said at some point during your talk, during your course, that you have some notes.
Yes, that's right. Yeah, well, I was saying, I forgot. I have to say, I will do it actually right now. I will send it to Sergio, and then maybe you can put it on the site of this conference. No? So these things are all in there, and a little bit more, but I didn't have time for that.
Well, if not, let's thank you not only for this conference, but for the 3 very nice conferences. Thank you.
You're welcome.